Hello everyone. Now we will continue our learning on simple reservoir simulation with MBAL software. Okay, so we are now inside the MBAL, and in this case we will construct a gas reservoir. Previously we learned many things about oil reservoir. Now we will learn about gas reservoir, and we will have gas injector also in addition to gas producers. Okay, so let's go ahead. Go to tool, material balance, and then go to options, reservoir fluid gas, and then tank model single tank, abnormally pressure no, production history by tank, compositional model none. As usual, you can provide user information, company, field, location, platform, analyst, user comments. Okay, and then click done. Go to PVT, fluid properties. Okay, so we will provide this window with gas properties, gas gravity, for example, 0.78, specific gravity, and then the separator pressure at which the measurement, the gas properties measurement is done. Okay, so the testing, the measurement is conducted at reservoir or at separator pressure of 200 psig, and then condensate to gas ratio, CGR, condensate per gas ratio, and the unit is stock tank barrel of condensate per million standard cubic foot of gas, all right, STB per MMSCF. The ratio is none, so we don't have condensate here. Condensate gravity, although it's 0, we still need to provide with data. So yeah, let's say 42. Water salinity, 10,000 ppm. And then no H2S, 0, no CO2, 0, no nitrogen, 0. Clear at all for gas viscosity modeling. And let's say I don't have any laboratory data. Okay, I don't know the pressure, Z factor, gas formation volume factor, gas viscosity. I don't know. I haven't done any laboratory testing, okay, for these properties. So I will rely on correlation. I will not perform PVT matching. I will rely totally on the available correlation. Okay, so we will leave it blank. That might be the case on the field. We don't have PVT data. We just have these parameters. We can still perform simulation. Okay, so don't be desperate if you have no PVT data. We still have hope. At least we can provide with these numbers. And for gas viscosity, we will select Lee et al. Okay, because we haven't done any matching, so we will not tick this use matching. Okay, it will be deactivated. That's okay. Click done. Now we will go to input, or we can double click here, tank one. Okay, so the properties of this gas reservoir, name tank one, or can also gas reservoir, temperature 250 degrees Fahrenheit with initial reservoir pressure of 5,500, okay, quite high. And then the porosity 0.2, Connaught water saturation 0.2, water compressibility 3 times 10 to the power of -6. Original gas in place. Let's say I know, okay? Let's say I know, and it is huge, 200,000, okay, let's say MMSCF, okay? So it's TCF in numbers, trillion standard cubic feet, okay? And then let's say for the production, January 1st, 2022, okay? And we will check the context, Okay, so we need to know the change of gas water contact. Okay, gas water contact. We don't have condensate, we don't have oil, we only have gas and water. And I want to know the increase or the movement of the gas water contact. Okay, all right. Let's say I know the dimension, the description, the geometry of my aquifer. I will model the aquifer with Hurst van Everdingen method, modified radial aquifer, and then reservoir thickness, for example, 100 feet, the thickness of my reservoir, and the radius of my reservoir with outer inner radius ratio. So the ratio of the radius of the aquifer and the reservoir. Outer means the aquifer, of course, the radial aquifer, and the inner is the gas reservoir. Okay, and then it is 5. Okay, I will put 5 here as per default with encroachment angle 180 degrees. And let's say the aquifer permeability is low, only 2 millidarcies. Okay, and then for rock compressibility, we will use correlation. Rock compaction, we will leave it as it is. We will not consider rock compaction. And pore volume versus depth, this is important if we want to monitor the movement of the gas water contact. And this is the note, pore volume definition. Pore volume is 0 at the top of the reservoir, and pore volume is 1 at the original gas water contact. So the depth of my top of reservoir is at 9,750 feet TVD through vertical depth, and then 50% of the pore volume at 11,000 feet, and 100% of the pore volume is at the gas water contact. It is at 12,000 feet. Okay, and then relative permeability, Corey function. Okay, if you select tables, then you will need to provide with more detailed like this one, but I prefer Corey functions to make my life simpler. Saturation, residual saturation for water, 0.2, like what I input in Conat water saturation, right? Whereas for gas, it is 0. And the endpoint or the maximum water relative permeability, 0.6, whereas for gas, it is 0.8. And the exponent is 1, so it will be linear. And if you want to check, you just plot. Okay. Okay. So yeah, the red line is for gas, so it is gas relative permeability versus phase saturation, or for gas, so it is gas saturation. And for KRW versus water saturation, the black line. Okay, you can also plot like this. So I will plot against water saturation. So it will be KRW versus water saturation and KRG versus water saturation. Okay, close. And let's say water sweep efficiency 90%, just in case. Okay, production history, I will assume this is a virgin gas reservoir, no production. So it's still virgin, no production, no injection. So no need to provide production data. I don't have production data, right? So no need for history matching. We just put the well, drill the well, and then forecast the production. It is a bit easier. So click done, or can also validate done. Okay, so this is our gas reservoir. We don't have production history. So if you open the history matching, everything will be deactivated, will be inactive, will be, yeah, you cannot enter each of this section because we don't have production history, so we cannot do history matching. So we go directly to production prediction, prediction setup. And now I will select this one, production profile using well models. Okay, so I will create well models and then I will forecast the production. Prediction start at start of production, which is January 1st, 2022. Options use fractional flow model. Prediction step size automatic. Usually it is monthly. Prediction end also automatic. Okay, done. And then constraints. Constraint is really important. So I will set the constraint at the beginning, the wellhead pressure or manifold pressure or system pressure to be 3000. Okay. And then in January 2025, I will lower down the system pressure to 2500. So I can extend the production life of my gas reservoir because the system pressure is lower, the back pressure is lower, so my gas can flow easier. And then I will have gas injection, so I need to put constraints to limit the injection. So it is at 2026. Okay, I will set the gas injection pressure. So not yet because I haven't put injector. So I will like this. Okay, I will deactivate it first. Click done. Later on, I will put constraint for my gas injector. Okay, and then well type definition, we will create well model for now. I will create one. Open the drop-down menu. Gas injector. I will call it gas gas injector. Okay. And then we need to provide inflow performance. I will use for Keimer. Fractional flow model will use tank, and Darcy factor for 460 and non-Darcy factor 0,00001. Okay, layers will be based on gas reservoir. Gravel pack no limit for maximum drawdown, no shift in IPR, and no permeability correction. Okay, if you want to plot, it is like this. Remember, we have gas injector, so the slope will be like this, positive slope instead of, as usual, negative slope. Okay, so it will be like this. Okay, as you increase the flowing bottom hole pressure or flowing injection pressure, you will get higher gas injection rate. Okay, close. More inflow, no need. Yeah, we can leave it as it is. Outflow performance. Okay, outflow performance. You can select constant flowing bottom hole pressure. If you want to put, it is a constant number, but it is not reliable because in reality, it is very difficult to get constant flowing bottom hole pressure. Okay, at any condition, at any water cut, at any reservoir pressure, at any dynamic condition, you maintain the flowing bottom hole pressure, it is unlikely to happen. Okay, so cancel. You can also estimate the outflow performance with Kullander-Smith method. You need to provide tubing length, tubing depth, wellhead temperature, bottom hole temperature, flow line roughness, tubing ID. All right, but I will generate the tubing performance curves with the data, the file from Prosper software. Okay, so we have created TPC, tubing performance curve, or VLP, vertical lift performance from Prosper, and then we can import like this, import, so that I can get the TPC for my gas injector. Okay, so I click import. All right. Okay, so this is the TPC file. Click open. Done. Okay, so this is the TPC, system pressure, manifold pressure, gas rate, and flowing bottom hole pressure. So if you plot, you will get like this. Okay, so this will be applicable for our gas injector performance. All right, we can finish. Done. Extrapolate TPC. Okay, so it will be extrapolated. Click done. Okay, so now I have my gas injector. So far, so good. So if we check the constraints, we actually need to have injection setting here. So let me check. Can we set? Okay, I think input, history matching, production prediction. Okay, let's just continue. And then I will create two producers. I will call it prod 1. It is dry gas producer. Okay. And then the inflow, the IPR, I will use for Keimer method. Fractional flow, use tank. Darcy factor 490. Make sure this is the unit, PSI square per MSCF per day. And for non-Darcy, like this. With this unit, no PI correction for mobility, and the rest, I follow the default. You can plot like this, the IPR. So the absolute open flow is 61.3 mmSCF per day, and the reservoir pressure is 5,500. Okay, more inflow. We can leave it as it is. And outflow performance, I will also get my TPC data, TPC result from Prosper. So I will import. Okay, so this is the TPC file for producer 1. Click open. Reading, 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 finished. Done. Plot. Okay, so this is our nodal analysis, the IPR versus, or the IPR plus VLP, or IPR plus TPC, tubing performance curve. You can maximize, or sorry, replot, maximize like this. Okay, finish, done, extrapolate TPCs. Okay, so far so good. Now, yeah, this is prod 1. I will move it there. I will add one more well type definition. It is also dry gas producer. Okay. And then inflow performance, it is 560, 0.0005, everything per default. Plot. Now the absolute open flow is 51.9. million standard cubic feet per day at reservoir pressure of 5,500. More inflow, outflow performance, edit. I will import. This is the TPC file for well 2, producer 2. Click open, finish, done, plot. Okay, so this is the nodal analysis for second producer. Okay, finish, done. Let's say I want to put constraint for my second producer. So the breakthrough will happen at water saturation, for example, the fraction 0.98. Okay, something like this in fraction, right? Okay, so far so good. Click done. I want to move my producer 2 there. Prod 1, prod 2, and injector maybe there. Yeah. Okay. And then, yeah, I want to check again. If you want, allow recovery after well abandonment. It's okay. And it'll also allow recovery for well abandonment. After abandonment, click done. Okay, so far so good. Now we need to set the well schedule. Okay, so for example, from the beginning of my operation at January 1st, 2022, I will drill two wells with the type of the well similar to producer 1. So prod 1 and prod 2, it's just a typical well. Okay, it's just a type of well. I can make prod 1 as much as 100 wells with the same characteristic, the same properties, the same IPR, the same VLP. Okay, so it's just a typical well. I can multiply the numbers of the well. And two wells, the prod 1, two wells will produce from the beginning of my simulation production till the end. And then I will drill also well, okay, but it will stop 2 years later, like this. So it will stop at 2024. 3 wells of producer 2. Okay, and we can check the production profile later. And then at this one, 2026, I want to drill 2 wells, producer 2. And then at 2026 also, I want to drill just one gas injector. So what will happen? Click done. Okay, let me check if I can change the constraints. Not yet. Okay. Yeah, we can set it like this, but actually we should be able to limit the injection. Okay. Let me check the prediction setup. Profile from production schedule. Production profile using well models. Okay. DCQ using well models. Okay. Calculate number of wells to achieve target rate. Hopefully we can also discuss this mode. Calculate number of wells to achieve target rate. Okay, and then manifold pressure per well, no. Oh, sorry, this one with gas injection. I should take this one, gas injection, to enable gas injection. So click done. We go to constraints. Now you see we have options for gas injection. And I will put constraint for my gas injection wellhead pressure or gas injection manifold pressure. I will keep it at 3,500. Okay. And then here, I just want to set injection gas gravity 0.65. Okay. I will keep the H2S, CO2, and nitrogen to be 0. Click done. Yeah, I think everything is okay. Now, yeah, just check the reporting schedule. It will be automatic, but it can be monthly, yearly, daily. Okay, I will set it to be automatic. Click done. Now just run the prediction. Calculate. Okay. You see, because we have huge reservoir volume, huge the gas in place, so the production will be to this one, 2,100. Very long, right? Gas recovery factor only 37%. It's quite low. It's quite low, right? Because we have gas water system, we have aquifer, so there will be water encroachment, which will hinder the production. Okay. Somehow we have oil rate, although it's very small, only 1 stock tank barrel per day. It is negligible. This is the gas rate. So we can achieve at the end of production 14 mmscf per day. This is the water rate. This is the gas injection rate. Also 14 mmscf per day. And then we maintain the gas injection pressure. Okay. Water gas ratio, gas formation volume factor, water formation volume factor, gas viscosity. Okay. This is the gas injection system pressure. It is constant at 3,500, whereas the manifold pressure changes from 3,000 to 2,500 at January 1st, 2025 as per constraints. Okay, now we can check the plot. We don't have history or simulation because no production data, but we have prediction. If you want to check the tank pressure like this, okay, so the pressure quickly drops because of production, but somehow here we have the drop is slower, okay, because the wells stop producing. Okay, I put the well schedule, some wells to stop at 2024. Okay, and then I put gas injection in 2026. So like this one, around this one, and the pressure quite stable. Not stable, but it is supported by gas injector. So the drop will not be this quick. Okay. And then gas recovery factor, again, you can only achieve 36%, 37%. I want to plot the gas injection rate, gas production rate drops quickly. And then we have new wells here. If I maximize, we have new wells here, right? But it stopped 2 years later, but increase again because we have new wells in 2025, but then the production stabilizes. You can plot it along with reservoir pressure, tank pressure, and gas rate. Okay. And also gas production rate and gas injection rate. You see, we start the injection at 2026. And because we put gas injection, I think it also has effect to increase the gas production rate here, along with drilling of new wells. P over Z. So you see it's not linear. Here it's linear, but then it turns to be curved because of water encroachment from aquifer, right? And you can plot, maybe we have aquifer influx. You see, because of aquifer influx, okay, again and again, we cannot have linear P over Z. And we want to plot the gas rate, water rate, water rate along with the aquifer influx. Okay, so the water comes also, the majority of the water comes from the aquifer. And some little portion of the water, of course, will come from condensation, but it's only tiny portion. And then you can also plot reservoir voidage and reservoir injection. Okay, and yeah, this is the analysis to get the balance between drawdown, between production, between withdrawal, and with injection. And then it can be summarized with this one, reservoir voidage balance. Okay, so it is not balance. Majority is production, production, production. That's why the tank pressure drops. But then it is quite balanced. Check the black dots. It is balanced between production and injection, quite balanced. So that's why the reservoir pressure is stabilized because of the balance between production and injection at this period of time. Okay, so that's for tank results. We can also check well results, either producer 1, producer 2. This is the producer 2, which stopped at 2024. And these are the producer 2, which start from 2026 till the end. And this is the result for gas injector. So first, prot 1, click plot. You can check the gas rate, number of wells, constant, 2 wells, flowing bottom hole pressure. Okay, flowing bottom hole pressure with tank pressure. Okay, because of the difference of reservoir pressure and bottom hole pressure, there is drawdown. So flow, gas flow can occur, can happen. Okay, the second type of producer, check the gas rate. It produced only for 2 years, starting from 2022, stops at 2024, January 1st, 2024. And then for the third type of wells, gas rate starting from 2026 till the end, 2100. And for gas injector, gas injection rate like this. Okay, so yeah, that's all. So in this case, we have created gas reservoir with aquifer, and then we create 2 producer wells, okay, 2 gas wells, and 1 gas injector. We set the well schedule, we drill some wells, we drill 1 injector, and we set the production and injection constraints, and we run the forecast, we run the prediction, and we get this result. Okay, So that's all. I hope you can learn more about reservoir simulation through this tutorial. Okay, see you again. Thank you.